Okay, so picking up where we left off last time. So we talked about Green's theorem, and I'll rewind just a bit here just to remind y'all what that is. So here it is. So we've made the observation that, wrong mode, that circulation is a quantity of interest, and we made the observation that it is an accumulating quantity. Once you know it's an accumulating quantity, you can compute it with an integral of a corresponding density, and the density turns out to be curl. So we did a few examples last time. So here is a nice application, and you can see that this is an application of Green's theorem because here's Green's theorem right there. Oh, by the way, I forgot to reminder attendance code, attendance quiz, time's clicking along, of course. So what we're doing here is we are applying Green's theorem to a special vector field. Now, it's not uniquely special. There are other vector fields that work just fine on this. But what makes it special, what we like about it, is that its curl is 1. And that means that this integral turns into just a double integral of 1. We're literally just adding up the little areas. We're just going to compute the area of the inside. So the wild result, pretty surprising, is that if you want to compute an area, you can just do this line integral around the boundary of the area you're trying to compute. It will compute area for you. Very weird, very unexpected, but it works. And again, Green's theorem is doing the heavy lifting here of making that work. Now, just as a notational point, this is one of the rare circumstances where I think the coordinate line integral notation is actually a little bit more compact, right? I mean, this is a little bit less to write down, a little bit more convenient in a way. So anyway, very often, usually when you see this written down as a theorem, they'll write it like this: integral x dy equals area. Now, reminder, 0 comma x is nice because its curl is 1. That's the sort of the necessary condition that we need for a vector field to make this work. But it's not the only such vector field. There's plenty of vector fields, right, that have curl equal to 1. And you can make your own version of this theorem, sort of an analog of this theorem, by just picking a different vector field whose curl is 1. The book has a different vector field that they use. They use minus y over 2 comma x over 2. And it works. And they get a different theorem. There's a different line integral that will compute area for you. It is more convenient in certain circumstances. I think, broadly speaking, this is the most convenient in most circumstances. It's certainly the most compact one to write down. It only has one term instead of 2 terms. So anyway, like I said, there's various different versions of this. Okay, so we want to compute an area. This is what we're going to do. Oh, wait a minute. We need to be able to compute these line integrals. How do you compute these line integrals? Well, if your boundary is made up of straight line segments, it turns out this integral is actually easy to compute. And in particular, when you have any individual straight line segment, then that integral is simple arithmetic. It is the average value of x on your line segment times the change in y over that line segment. That's it. Simple arithmetic, right? Just like you see here, right? Super easy. No calculus. Once you have that formula established, you don't even have to use calculus to compute that integral. Now, I do think this is a good exercise. I think everybody should do this. A good practice problem. Just parameterize a line segment and compute this. That is, compute this. Brute force, just pull back through the parameterization, right? It's just plug and chug, in other words. And when you're done with that chugging, you will have proved this result. So give that a try. Again, it's a good exercise. Let's see how we can use this in practice. Here is an example. You notice our boundary here is, in fact, made up out of line segments. Right? So we've got 9 line segments there. And all together, if you want to compute the area going around the boundary, integral x dy, just take that as a sum, right, over all of these individual line segments. So, for example, there's the first one. Compute integral x dy on that line segment. When you're done with that, now compute integral x dy on that line segment, etc. Just keep going all the way around. And the arithmetic, again, very straightforward. So let's look at, for example, let's look at this first line segment, I equals 1. On that first line segment, we start at x equals 1, we end at x equals 12, and the average of those is 13 halves. Snap, nothing to it. Likewise, on that same line segment, we start at y equals 1, we end at y equals 6, so delta y is 5. Nothing to it. Orientation matters, so keep this in mind. This edge is going that direction, so in particular, y increases because we start at the lower value and end at the higher value. For some of these other edges, you're going downward. Their delta y would be negative. So, then per this formula up here, which I've recopied right there, you can multiply those numbers, and there's your first term. And that's for that first edge. And notice that, again, it was just a simple little arithmetic. And then, okay, well, a little bit more arithmetic, right? You do have to do all 9 edges, and you make yourself a little table here. And it's, you take a deep breath and plow forward, and it's ultimately just not that bad. Anyway, there's an answer. And it's, I think, a way better alternative than if you were to try to brute force this. If you were to take a high school geometry approach to how would you compute this area, let's just go down that road a little ways just for the horror of it all. I would say, well, there's a triangle there, and there's a triangle there, and likewise maybe here. And, oh gosh, maybe we'll do one like this, and then there's another one like that. Notice none of these triangles are right triangles. So you're going to have to compute edges, but you're also going to have to drop perpendiculars, and I think that's going to be a nightmare of inconvenience. Right? It's really quite a nasty little problem, even though it's, in fact, just computing area. How we doing? Everybody all right? Okay, nice little application. And again, the thing that makes it work, the thing that, where the magic happens, right there, Green's theorem. Okay, next nice little application. Let's talk about flux through a curve. Flashbacks to chapter 3. Y'all remember flux through a surface from chapter 3? This is a kind of analogous idea. Instead of having a surface in space and having a 3-dimensional fluid flowing through that surface and us wanting to compute volume per unit time, here we're in 2 dimensions. We have kind of a 2-dimensional fluid flowing along. And I want to know the amount of area of fluid per unit time is passing through a curve. Right, so just like in chapter 3, but 1 dimension down. Okay. This is a very nice exercise. The way I would suggest you do this exercise is to go back to chapter 3, shamelessly rip off that computation, adapt it accordingly, of course, and what you'll find is that the area of fluid per unit time passing through that line segment is given by this formula right here. And you'll even notice the formula is analogous. In the 3-dimensional case, it's F dot n times the area of the surface. Here, same, just length of the curve. Plausible? Everybody buying it? Again, I know I give you all a lot of these suggested exercises, but I do think it's a very nice practice problem. You'll learn from the process. Okay, so here we're going to consider a kind of a generalization of this. What if not only we don't have a straight line, but what if our curve that we're interested in is like a boundary of some region? And I want to be able to talk about the flux through that boundary curve. Natural question that comes up, which way are we talking about? Right? When you have a curve that is a boundary, and remember this term boundary, loaded word. In chapters 6 and 7, boundary always means oriented according to a specific arbitrary but standard convention. Right? So we have a arbitrary but standard convention here. Boundary means oriented outward. So our normal vector always outward, away from the region. That's just this arbitrary but standard convention. Okay, so how will we add this up? Well, I would look at one little piece at a time. Let's see, I'll use blue. I would look at, for example, this little piece of curve. I would ask how much flux is there through that little piece of curve. On that little piece, I would write down the formula from the previous page because it's approximately straight, right? And so I've got this integral here, and the big question that comes up next is how am I going to compute this integral? You probably have noticed this is not a familiar looking kind of integral. We've seen line integrals of vector fields, but it's always been f dot t ds. We have never seen f dot n ds in an integral. So what are we going to do about this? All right, there's a great answer to this question. It's a very clever little move. Reminder, let's see here. Let me color code this. So we've got f dot n. We've got our vector field. In other words, there's our normal vector. We're interested in that dot product, f dot n. Here's the clever observation. Very clever idea. If I were to take both of these vectors, just rotate them both 90 degrees counterclockwise. Right, so 90-degree counterclockwise rotation. Notice my normal vector turns into my tangent vector. Isn't that nice? My P comma Q field vector, well, it's gonna turn into something else, but we know how to do 90-degree rotations of vectors. Flashbacks to linear algebra, linear transformation, matrix, columns are the images of the standard basis vector, all that jazz, right? And P comma Q turns into minus Q comma P. Make sure you can do that. Again, I know I say that a lot, right? But definitely make sure that you're good with why that's minus Q comma P. If you get stuck on any of this stuff, as always, come talk to me. I'm very happy to help. Make sure that you're good with why that is. So punchline then, if you think about it, let's look at these two vectors now. F perp and T, let's think about their dot product. Well, those two blue vectors have exactly the same magnitudes as those green vectors. The angle between the two blues is exactly the same as the angle between the two greens. That blue dot product is the same. And so if you want to compute that green dot product, we do so, we do so with the blue dot product. And this little clever little move that we just pulled off has turned an integral that we've never seen before. What's the deal with this dot in ds into a good old chapter 5 style TDS, regular old vector line integral. Is that all right? Everybody okay with what happened there? This little rotation argument is very clever. Okay, and it's home stretch at this point because we know how to compute. Keep in mind TDS is dr. We know how to compute vector line integrals, one of our big tools, Green's theorem that we talked about last time. So there it is. We're just going to take the curl of this thing called f perp. Now, I'm going to go back here to where we wrote down the formula for curl. Here it is. The formula for curl, dq dx minus dp dy. Do be careful with this formula. When we say dq dx, this doesn't mean whatever in the problem happens to be called q, right? It means whatever is the second coordinate of the field whose curl you're computing, right? So x partial of the second coordinate minus, and then likewise y partial of the first coordinate. So with that in mind, let's see here, and I need to get all of this onto the screen at the same time. To compute curl, compute curl here, curl of f perp, I need the x partial of the second coordinate of f perp, which is p, not q, minus the y partial of the first coordinate, which is minus q. Everybody see what happened there? Easy to mess that up. Okay. Now it's all over but the shouting. These two minus signs cancel. You end up with that, and then you notice, oh my gosh, totally familiar. That's in fact divergence. Right, this a formula we wrote down back in chapter 3, right? And coincidentally, so it would seem, it just kind of pops up here. And that gives us our theorem. So our theorem, again, if you want to compute outward-oriented boundary flux, you can do so with a double integral of divergence over the interior. And let me remind you, we just walked through it, but let me emphasize, Green's theorem is what made this argument work. Right? That's where the heavy lifting happened. This is where the magic happens. Everything beforehand is just kind of rewriting things in clever ways. Everything that comes after is just kind of the computation of the coordinates. Most of the work, most of the power of what just happened is Green's theorem. So a lot of people call this a variation of Green's theorem or sort of an alternative Green's theorem. I'm going to write it here as the two-dimensional divergence theorem. It's also very commonly known as the two-dimensional divergence theorem. All right, is everybody good? Okay. Let's do one. Question says compute the flux. Now, it says integral f dot n ds. Okay, well, sure, integral f dot n ds. And that is, again, just one way to write flux, which we are going to compute as a double integral with divergence. So, you see right here, flux, double integral with divergence. Divergence is easy to compute, right? We take our vector field, we compute the appropriate partials. The divergence ends up being -3. We have an easy double integral victory. Nothing to it. Everybody happy? Okay, here's a different take. I think this is really nice. And I think it's important too. So I'm perfectly happy with this argument connecting, basically allowing me to take Green's theorem and kind of turn it on its side, and out comes a two-dimensional divergence theorem. But again, the heavy lifting done by Green's theorem. Green's theorem is a statement about accumulations, specifically accumulation of boundary circulation. But here's the thing. Flux accumulates also. We don't need Green's theorem to do this. I can make an argument. I'm going to show you the argument right now. I'm going to argue that boundary flux is an accumulating quantity. And once you know that boundary flux is an accumulating quantity, here's how you can think about the two-dimensional divergence theorem. Once you know it's an accumulating quantity, you can view it as a stuff, you can imagine the corresponding density, you can compute it with an integral of that density, and you get the two-dimensional divergence theorem as an accumulation result on its own. So let's not get too far ahead of ourselves here. Let's talk about why this is an accumulating quantity. We imagine a hole. We're going to look at the boundary, talk about flux through that boundary. Flux through that boundary would be outward oriented. On the boundary curve. So there's the whole boundary flux. Now let's look at the parts. For this left part, here's the outward oriented boundary flux on the left part. We'll look at the right part. Here's the outward oriented boundary flux on the right part. And as usual, we have the question, is blue plus green equal to purple? Right, there's our question. Again, the casual, careless glance says, well, we got this problem on this shared interior edge. I see green and blue. I don't see any purple. What's going on there? I see over here on the right, I see blue and purple tracking each other perfectly. That's a matchup. That's fine. Over here on the left, I see green and purple tracking each other perfectly. Perfect. Great. Super. But after we get rid of the stuff that we sort of know is doing what it's supposed to be doing, I do have this problem of I have that shared interior edge, and I've got two flux integrals across that shared interior edge. That's our problem. That's our discrepancy. That's what's between us and victory. And it's 0. And by the way, let's take a quick moment to recognize the reason that this is 0 is because we're looking at an edge appearing twice but with opposite orientations, and so they cancel. And when we looked at Green's theorem for the first time, we had an edge that appears twice, not with opposite orientations through, but with opposite orientations along. Right? Still opposites. Just this was along, and this is through. But very, very analogous. And by the way, we're going to keep noticing this pattern. This pattern is going to continue with several other theorems that we're going to talk about as we continue along through chapter 6 and 7. So our problem goes away. There is no problem. And boundary flux is an accumulating quantity. Everybody happy with that? Okay. Now again, a little bit of terminology. I like emphasizing the analogy. I think the analogy is very strong. I like to make the case that when you have an accumulating quantity, circulation, for example, accumulating quantity, flux, we just argued, is an accumulating quantity, they're going to behave a lot like mass. They're going to behave a lot like a substance, even if it's not physical. It doesn't matter that it's not physical. It behaves in the equations like a substance, so we can pretend it's a substance. And it works just fine. So this computation about mass that we started doing in early chapter 5, and it's totally familiar, and mass is an integral of mass density, well, sure, why not? Well, circulation is an integral of circulation density, and flux is an integral of flux density. And so these two sophisticated, intimidating, hard to visualize theorems, yeah, it's kind of the same as that. If you're willing to accept, if you're willing to play along with the idea that accumulating quantities are kind of a substance. All right, now again, terminology. Y'all are, of course, familiar with the term mass density. Of course. Yeah, sure. Why do we call it mass density? Well, because mass is the accumulating quantity for which this is the corresponding density. And I've made the case previously that, well, likewise, we call curl circulation density, well, because circulation is the corresponding accumulating quantity that we're treating as a stuff for which this is the density. Well, you can see this coming. We're going to call divergence flux density because flux is the stuff. It's the accumulating quantity. It's the substance-ish thing for which divergence is the density. And FYI, this term right here, very common. This is not me, trying to popularize my own little personal narrow take on something. This is an extremely broadly used, broadly circulated term. In my own physics classes when I was an undergrad, I heard my physics professors say the term flux density more than I heard them say the term divergence. For your consideration, right? I'm betting that your engineering professors are some of them anyway, who knows, right? But very well could also be big users of this term flux density. You're definitely going to see it around here and there. Okay. Everybody okay with that? And by the way, this term circulation density is not as common, which I think is super weird. It makes just as much sense. It's just as descriptive and explicit and fits. The analogy is just as strong, and yet you don't hear that term as much. I think it's a shame, right? I credit this term with helping me as I was learning this material to get this point of view and to understand the divergence theorem, because the term was so explicitly descriptive of the role that divergence was playing. It was super duper helpful to me. I really wish that someone had used this term for me as I was learning Green's theorem and a related theorem that we're going to see later called Stokes's curl theorem. Anyway. Okay. Moving along. This next couple of pages is I think a really valuable point of view. I'm going to set up an analogy to something that you're all already familiar with. And as you all know, I'm a big fan of this idea. If you're trying to learn this concept, but you're already extremely comfortable with this concept, any analogies and comparisons that we can set up between them will allow you to take your existing understanding over here and just be like, okay, well, what I'm trying to understand, it's totally analogous to this thing over here that I already get. And that's an extremely helpful point of view to help you extend those ideas. So I'm going to give you a different take on the fundamental theorem of calculus that I know y'all are already very comfortable with. The theorem, that is. The take I want to give you is that the left side of the equation, right, f of b minus f of a, right, that y'all have all known about for a long time, I'm going to call it change. And guess what? It is an accumulating quantity. So the fundamental theorem of calculus that you already know, that you're already familiar with, that you're all kind of semi-experts at, is totally analogous to all these fancier, scarier theorems that we're in the process of learning. And so what we're going to do here is we're going to figure out, okay, what are the different roles that the different players in the fundamental theorem of calculus, what roles do they play? How do we think about those things? And then, again, by analogy, that might help you to get used to or get comfortable with analogous roles of analogous players in these other theorems. So here we go, accumulating quantity. Stuff is stuff per unit size times size. Now, of course, size is just length because we're looking on intervals, one-dimensional intervals. So that suggests that I can think of the derivative as being a density. Isn't that weird? Right? The first time I thought of it, by the way, no one ever showed me this. I had to kind of figure this out for myself. But you can think of the derivative as being a density. And it makes perfect sense if you kind of think about the picture. Let's think about how do we think about a derivative? We think about a derivative, looking at a graph anyway, as kind of rise over the run. There's the rise. There's the run, right? So green over blue, rise over the run. Well, here's the thing. This green represents, over this little subinterval, how much did the function change? How much of our accumulating quantity do we have, in other words? It's a kind of a stuff. That numerator is a kind of a stuff, if you're willing to think of it that way. And the run here, well, that is, of course, the size of that little subinterval. So this is stuff per unit size. That is what density is. I'm going to propose that for our purposes right now, you should think of the derivative. Don't think about it as a slope. Don't think about it as like a speed or velocity or anything like that. Think of it as a density. Is that cool? All right. So there's two things we're going to do with this. I'm going to start by going back to, let's see, where's a good picture? Yeah, we'll use this one. It's fine. There is a weird ask. Actually, you know what? Maybe this is, let's go with this one. I think this will be better. A weird ask that I put out there a while ago was that boundary circulation, wrong mode. Boundary circulation, again, kind of going around like this, line integral as I go around like so. Because it's an accumulating quantity, you should think of it as a substance in the interior. Now that's not what the picture suggests. Look at the calculation for boundary circulation. The calculation happens on the boundary. The whole calculation is on the boundary. I'm asking you to view it as something that's actually in the interior, even though it's clearly computed on the boundary. What gives? Right? That's very counterintuitive, and I want to acknowledge that's a very strange seeming suggestion that something that's clearly computed on the interior could ever be possibly thought of as happening. I said that backwards. Something that's clearly computed on the boundary could be thought of as happening in the interior. Now let me try to persuade you that this is not such a big ask. Let's think about the analogous statement here with the fundamental theorem. And let's look at change. How do we compute how much the function changes? Well, we look at the boundary, don't we? It's f of b minus f of a. And so we compute change with a computation that happens on the boundary. Where does change actually happen? Of course it happens in the interior. Look at the picture here. You can see the function changing. The function clearly changes not only in the interior between A and B, it happens very specifically in this case on a certain subset of that interior. That's where the change happens. You can watch it happening. Is that cool? Everybody with me? So, I think this is a very shocking observation that what seems like a nonsensical ask back here, boundary circulation. Come on, it happens on the boundary. How can we think of this as happening on the interior? There's nothing strange about that in this context, in this highly analogous context. Of course change happens in the interior. So I'm going to encourage y'all to kind of chew on that a bit. Try to try to ask yourself, for example, if I'm super comfortable with the idea that functions change over the interior, that change that I measure on the boundary happens in the interior, why not for circulation? Also, totally analogous stuff. Something to chew on. Okay, the next thing I want to point out is that the density, the derivative in this case, the density points specifically to where and how much that quantity is happening, right? This change in this case, but the accumulating quantity in question called change, the derivative points to where that is happening. And here's a nice numerical example right here. We've got a function and an interval, 0 to 3. How much does that function change on that interval from 0 to 3? Well, it changes by a total amount of 9. Where does that change happen? But more to the point, there's going to be more of it happening on some of the interval and less of it happening at other points on the interval. Between these two candidates, looking at 1 and 2, a couple of points inside of that interval, where is more of that change happening? Now, y'all, of course, could just look right at the picture. So let's not cheat and let the picture answer the question for us. Let's try to use the derivative. Let's try to use the density to answer this question for us. If you want to know where more change is happening, we will look for the change density. The change density is going to tell us whether there's more change happening here or more change happening here. That change density is the derivative. The derivative is easy to compute. I can then plug in 1 and 2. And entirely without the picture, right? No geometric intuition. Oh, well, it would seem that at x equals 2, there's more change density. So I think there's more change happening in the general area where x equals 2 compared to x equals 1. Does that make sense? Seems like a reasonable conclusion. And then, of course, the picture corroborates. And you can very much see that, let's see here, that there's a little bit of change happening there, but there's more change happening over here. So densities tell you where this thing that we measure on the boundary, where specifically and how much is happening where in the interior. Okay, so let's see this applied to curl. And let's see, well, let's look at, we've got this rectangular region here. That rectangular region has a certain amount of boundary circulation. And I'm going to draw its boundary circulation like so. Boundary circulation is computed as a line integral like that on that boundary. So that's where you measure. That's where you measure that boundary circulation. But again, we've already discussed, just because you measure it there, that doesn't mean that's where it's actually happening. I claim this circulation that we see on the boundary is actually coming from the interior. And I claim that curl is going to tell us where it's happening. So let's think through some particular points of interest. Let's think about, for example, let's say a point right there. Now, quick reminder, remember circulation is a way of measuring how, if you've got a fluid flowing and if you've got a little small floating object, in my mind I think of a leaf, fall color, why not? Got this leaf that fell in the water. How is that leaf going to be rotating? Right? Circulation is a way of saying how that's going to sort of rotate as it floats downstream. Of course it'll float downstream, but as it floats, how will it rotate? And I would point out here that the fluid is pushing on sort of the top side the same amount that it's pushing on the bottom side And I feel like this leaf wouldn't really be rotating at all to speak of. Does that seem reasonable? Okay, so now if you were to compute the curl, anywhere in this region here, in this sort of the upper sort of part there, that sort of white background upper part, if you were to compute the curl, you would get 0. And something very similar happens down here. Very similar. Now the big difference is these field vectors are longer. So there is, of course, a greater flow, so it's getting pushed harder on its top side. It's getting pushed harder on its bottom side, but it's still being pushed the same on both sides, right? It's like when you're at the grocery store and you have the cart, and you hold on to both sides, you're pushing both sides the same, the cart goes straight, right? But if you let go and you're pushing more on the right side with your right arm, but you're not pushing it all on the left, the cart's going to start to turn. Right? Pushing it more on one side will make it rotate the other direction. So in the middle in here, we can actually see that happening. Let's see here, in this sort of gray region here. In there, let's look at a leaf, let's say here. And well, it's being pushed on both sides. On the top, it's being pushed, but not very much because the field is weaker there. And then on the bottom, it's being pushed harder because the field has grown. You can see this vector field as I have it drawn. It's getting stronger as you move down in here. This leaf is going to have an experience kind of like the grocery cart. It's being pushed on one side more than the other, and I propose that leaf will rotate. And I would propose it would rotate counterclockwise, as I've got it drawn here. Is everybody buying it? And if we could write down a formula for this, which, by the way, I didn't write down formulas for this. I just wanted this to be kind of a geometric, kind of intuitive sort of a discussion. But if we did write down such formulas, and if we were to compute the curl in here, what we would find is that the curl is positive. Positive corresponds to counterclockwise for curl. So keep in mind, curl is based on circulation. Circulation is based on boundaries. Boundaries, arbitrary but standard, boundaries are thought of as counterclockwise. How are we doing so far? Everybody all right? So I claim curl is telling us where this circulation is coming from. So again, if I look at this, sort of the big picture here, I've got, let's see, there we go. I've got all this circulation. I see the circulation. I measure the circulation on the boundary. Yeah, but where did that circulation actually come from? And I say the circulation actually came from there. That's where stuff is rotating. All the rotation that we measure around this outer boundary is really a consequence of what's happening in this gray region. It's a consequence of what's happening where the curl is positive. The curl is pointing explicitly to where that circulation is actually coming from. In exactly the same way that the derivative here is pointing to where all the change is coming from. Different accumulating quantity, different density, different geometry. Same basic ideas. So, all right with that? Okay, likewise for divergence, keep in mind divergence addresses the question of where flux comes from, and if you were to imagine some little region, for example, let's say here, notice there's just as much inward flux as there is outward flux. There's no flux coming from over here. Flux is 0 over here. Divergence is 0 over here. Looking over here, there's less inward flux. There's less outward flux. But again, same amounts. And so, again, net flux, total boundary flux there on that little green region. Again, 0. No flux. No divergence. And what we would find, you can see it by looking at a little square like this. That little square, there's a small negative amount of flux. There is a larger positive amount of flux. Here we would measure a positive flux. We would compute that with a positive divergence. And that's telling you where all the boundary flux is coming from. The boundary flux is coming from where the divergence is. And let's see here. So we would compute the flux outward on the boundary, but where the flux is actually coming from is in the interior, right where the divergence says it's coming from. Okay. All right, and y'all can make this algebraic by here's an explicit example. And again, if you want to know where is circulation coming from, we look at circulation density. Circulation density is curl, easily computed. Compare our 2 points. See what the circulation density is at those 2 points. Wherever it's bigger, that's where more of it's coming from. Just kind of an algebraic and numerical equivalent. Likewise for flux and divergence. All right. So the last thing I want to talk about in this section is how to deal with singularities, and we have 3 minutes left. I'm just going to get started on this, plant a thought. We're going to end this example with we're going to end what we're going to do today on this example with a lot of big questions, and we'll deal with those next week. But we're going to look now at this vector field. Notice the stirred pot, minus y comma x. But notice now that we also have a denominator. That's going to make this sort of, more circulation happening near the origin and less, the further you go away from the origin, the smaller these field vectors are. But in particular, we have a singularity at the origin. The vector field is not defined at the origin. So you can compute the curl for this vector field. You'll get 0. That's nice. No curl. And not at the origin, of course. At the origin, we have no idea what's going on. It's not even defined. We can't compute curl when it's not even defined. But there is this question of, okay, well, if the curl is 0, wouldn't Green's theorem, if the curl is 0, wouldn't that kind of suggest that we should get 0 for a line integral? So, for example, this line integral here, tempting to say, well, that line integral, I think I ought to be able to compute that as a double integral of curl. The curl is 0 everywhere. Well, okay, not at the origin. We've got that one little itty-bitty, little annoying, little trivial, one little point. That's a problem, but come on, how much of a difference can 1 point make? And we might think that 1 point is irrelevant. We might conclude sloppily that the integral ought to be 0. But it's not. In fact, what you will find is that integral is, depending on the curve, but for that one that I have indicated there, that integral is 2 pi. And so what we're going to have to do next time is we're going to have to figure out, okay, apparently Green's theorem doesn't apply. Apparently one little singularity point makes the whole project crash and burn, right? We should have gotten 0. We didn't. Clearly this doesn't work. So how can we fix this? How should we think about the singularity? And is there a way to kind of recover this idea that can I still think of circulation as being a kind of a substance? And can we sort of recover a way to make sense out of that? We'll answer that question next time. Y'all have a good weekend. See you later.